the section on primary voltaic cells and secondary voltaic cells, as well as electrolysis, I'm going to skip. As long as you know the main difference between a primary and secondary voltaic cell, as well as electrolytic cells, you will be fine for the AP test. But pages 12 through 14 basically go through examples of these types of cells, and you won't see those. So we're going to skip to page 15 and Faraday's law of electrolysis. Michael Faraday was the first to observe that the amount of substance undergoing oxidation or reduction at each electrode is directly proportional to the amount of electricity that passes through the cell. We're going to define the gram equivalent weight of a substance that is oxidized or reduced as the mass of the substance that reacts or is formed when 1 mole of electrons is transferred during the reaction. The quantitative unit of electricity called a Faraday is the amount of electricity that reduces 1 gram equivalent weight of a substance at the cathode and oxidizes 1 gram equivalent weight of a substance at the anode, which corresponds to 6.02 times 10 to the 23rd electrons. But a smaller unit of electricity is commonly used. It's called the coulomb. 1 ampere is 1 coulomb per second. So Faraday's law states that during electrolysis, 1 Faraday of electricity reduces 1 gram equivalent weight of oxidizing agents and oxidizes 1 gram equivalent weight of reducing agents. Let's look at some problems involving Faraday's law. We want to calculate the weight of copper produced by the reduction of copper 2 ions. So the first thing we need is our equation. So we've got copper 2 ions that are being reduced to form copper. So this is at the cathode where reduction occurs. So we have 1 mole of Cu2 plus ions plus 2 moles of electrons forming 1 mole of copper metal. If we look at masses, 63.5 is the molar mass for copper. For electrons, we've got 2 moles times 96,487 coulombs. So 63.5 grams of copper are going to plate out for every 2 times 96,487 coulombs of electric charge based on the half reaction that I've given. So to find the number of coulombs, here's what we would do. To find the number of coulombs, this is going for 45 minutes. So I'm going to take 45 minutes. There's 60 seconds in 1 minute. And 2.5 amps, which means 2.5 coulombs per second. So the number of coulombs, 6.75 times 10 to the third. And again, an amp is a coulomb per second. Now to find the number of grams of copper, we're going to take the amount of coulombs, 6,750. For every 1 mole of electrons, there are 96,487 coulombs. Now go back to the half reaction. We had 2 moles of electrons for every 1 mole of copper. And we know that copper's molar mass is 63.5 grams per mole. And you can see how these units all cancel out. So the mass of copper that will be plated out is 2.22 grams. So that's how much copper will be plated out for 45 minutes. Let's look at another problem very similar to the previous one. But now we're looking for the volume of oxygen produced by the oxidation of water. So what we need again is the half reaction. Go back to the electromotive series, and the half reaction looks like this. So there's the half reaction. This is oxidized, so this is the anode. We want to get the volume of oxygen. If you look at the half reaction, we've got 1 mole of oxygen for every 4 moles of electrons. At STP, 1 mole of oxygen occupies 22.4 liters. We have 4 moles of electrons. That's 4 times 96,487 coulombs. Okay, the first thing, just like we did in the previous, find the number of coulombs. This is going for 45 minutes. (60 seconds per minute). And it's 2.5 amps, which is 2.5 coulombs per second. And so just like in the previous problem, we have 6,750 coulombs produced in 45 minutes. We want to find the volume of oxygen. So we're going to start with the amount of coulombs. (6,750). 1 mole of electrons is 96,487 coulombs. From the half reaction, we had 4 moles of electrons for every 1 mole of oxygen. And 1 mole of oxygen occupies at STP 22.4 liters. We're assuming an ideal gas behavior. So the volume of oxygen at STP produced is 0.392 liters.